What's going on, guys? Welcome to episode 3 on our series of differential equations. Tensor fields, conservation laws, and geometric formulation is essentially the topic that we'll be covering. And this is related to the idea that physics is invariant. Physics is the same no matter how we choose our coordinates. And while our grids and labels are these kind of artificial tools that we've created, we're going to try to escape this Cartesian world that we explored in the previous episodes. And we're going to dive into curved spaces, conservation laws, shocks, exterior calculus, and even geometric optics, and show how they're all related. So conceptually, that's basically what that's the goal of this episode. And I want you to be able to walk away from this with the ideas to come to life, and by the end you'll see how all these pieces connect to form a unified coordinate view, a coordinate-free view of physics. So again, we stuck to Euclidean spaces in the previous episodes, and you can think of this as like flat, simple x-y coordinates. We treated partial derivatives on these coordinates as fundamental. But the reality, the real world isn't flat, okay? You can imagine a hurricane, right? Swirling on Earth's spherical surface, and we need to, the weather guys like solve that, you know what I'm saying? Or a stress in a bent steel beam, or warp space-time near a black hole, right? These can't be captured with the Euclidean space, right? So to handle this, we need to reformulate physics onto spaces which we'll call manifolds. And these are spaces that look flat up close. Okay, as we zoom in really, really closely, it looks flat locally, but they actually curve overall. And the key upgrade that we get from this is we can replace ordinary partial derivatives with covariant derivatives, and this keeps equations true no matter how we twist our coordinates. And this sounds really abstract, but I'll show you what this looks like geometrically and visually. But this detaches from grids. And lets physics shine through invariantly. And we can realize that the map itself isn't really the territory, but the coordinates themselves are just kind of our way of navigating through this. If you want a more rigorous treatment of this, I have the initial conditions, which talks about atlases and charts, and compact topologies and all this stuff. Okay, but essentially, what this is an applied. This is an application to differential equations and to describe physics, okay? So, again, we're going to show how derivatives map to curvature, how conservation laws hold in wavy systems, and how geometry will emerge from the waves themselves. So, standard partial derivatives, they fail on curved spaces because we compare vectors at nearby points without considering how they bend, or just any bend between. So, this allows us to define something called the covariant derivative, which fixes this with something we call an affine connection. So on a manifold M, the covariant derivative nabla sub x acting on V tells us how a vector field changes along direction x. And in coordinates, it is the partial derivative. It's really just the partial derivative plus this correction term, which we'll call the Christoffel symbols. Okay. And this gamma term here will capture how the coordinate system twists. So for spaces that contain a metric, like distance measurements or whatever, Minkowski space or any kind of space, we can use the Levi-Civita connection from 1917. And it was derived purely from the metric tensor G. And there's no more assuming flatness. Essentially, we don't have to assume flatness anymore because this makes derivatives covariant, meaning that they will transform properly under coordinate changes. So the covariant derivative along a curve gamma is said to be zero. If it is, if it's zero, then it is said to be parallel transported. So on a flat space, this means that the vector stays the same, but on curves like a sphere, dragging a vector along or around a loop brings it back rotated. And this idea encodes something called holonomy. So if we were to just start from this, if we were to take this vector that's pointing this way, and if we were to just kind of transport it slowly along the loop here, as you can see, as it progresses along the path, it comes back completely rotated 90 degrees. Okay, so it is rotated a positive, a counterclockwise 90 degrees, and this is what we call the holonomy angle at closure. Okay, for a closed loop. And again, this shows, really pay attention to what you're looking at, because it shows a sphere, right, with a closed triangular path from North Pole to equator and points back. And again, it stays parallel locally on the manifold, but it rotates overall. So the initial, I mean, think about the consequences of this. If you were at the North Pole, right, and you face the same direction, but you just did a little closed loop, you would find out that you will have rotated 90 degrees. Okay? And, you know, the holonomy equals this solid angle that's enclosed by the loop itself. Okay? Mathematically. And this isn't the vector's fault, because it's the sphere's curvature. Okay? If you play with it, so if you change the angle, you can see that this final rotation, again, will persist. And this connects directly to our theme, right? Curvature twists in naive expectations, and the covariant derivative will try to account for that twist. Okay? Holonomy isn't just like fun, right? It's key to general relativity and gauge theories. So now we're going to link this concept to conservation laws, where transport, right, ideas, parallel transport, they appear in how quantities flow without grids. All right, so for example, conservation laws. Okay, physics boils down to conserve stuff, right? Mass, momentum, energy. So these actually aren't partial differential equations first. They're actually integrals of motion, right? And what these allow us to do is say, you know, what goes in must come out, and they're invariant to coordinates. So a basic conservation law for density, right, and flux would just be the temporal derivative with respect to the density is equal to the nabla, or the divergence of that flux. Okay, and for hyperbolic systems like waves, this is really the divergence form that encodes the information traveling at finite speeds along characteristics. And characteristics, again, are a way of turning partial differential equations into linear ODEs. These are paths where the equation simplifies to an ODE, right? So if we look at the Inviscid-Burgers equation, this is a very simple nonlinear wave model, much like the Riccati equation. It's a good analogy. The wave speed is u itself. The taller parts will move faster of the wave, and it steepens the wave until it breaks at some time t sub b, or time of break, where the derivatives will blow up and form a shock. After the break, we can use weak solutions, or the integral versions of the derivative, right? But they're not unique. Again, and the uniqueness was determined by the Fredholm theory, index theory that we talked about earlier, but in the previous episode. But we pick the physical one via the entropy conditions that were discovered by Lax in 1957, or vanishing viscosity. Okay, so shock speeds, the shock speed S follows something called the Rankine-Huguenot condition. Hopefully I said that right. And it looks like this, all right, where it's just a difference. It's a finite difference. So let's look at the solution to Burgers' equation for a shock condition. All right, we can start with a smooth sine wave, okay, and we can watch this wave kind of like steepen and steepen and steepen, right? So again, this is the shock wave that is happening, and we'll get a vertical jump, and the shock will snap. Essentially, we'll get a snap, and that vertical jump is encoded how a tiny diffusion, a tiny piece of diffusion will select this entropy condition that was entropy solution that was solved, or that was shown to exist. Okay, and so we can also, again, encode it into these solving these partial differential equations and curvature itself are entropy and conservation. All right, that's a really important thing to talk about. So pre-shock, it's smooth, right? It's very smooth. Post-shock, it satisfies this equal area rule that was that the area under the curve must balance, and this demonstrates the idea of nonlinearity creating discontinuities, just like the analogy to the Riccati solution, right? Even from smooth starts. So notice the connection to our earlier theme. The shocks are like curvature in solution space, and the naive derivatives will fail. So we need integral forms to proceed invariantly. And again, this conservation, the idea of solving differential equations with conservation, links geometry via forms, all right? Which we'll explore next in exterior calculus. But again, the shocks or the singularities, or the blow-ups are unphysical, and really we need a way to reconcile the artifacts of our coordinate systems to solve these partial differential equations, okay? On manifolds. So tensors are really messy because they have this whole indicial, there's these very general objects that encode operations from multilinear vector spaces onto other multilinear vector spaces, or just, vector spaces or scalars, right? So they're very messy, but exterior calculus will allow us to give a clean index-free way to handle geometry and integration. So if we look at differential forms, we can swap vectors for differential forms, and they are things that are built to be integrated. So if we look at a zero form, the scalar function f it's just a scalar. That's what we call a zero form. A one form is basically a line integral, all right? And again, they're just built to integrate. The two form is what we call a surface integral, or just integrate over a surface. And the wedge here has this antisymmetric property that makes it, essentially, it bakes in the idea of orientation, right? Oriented surfaces, areas, and volumes, okay? And so what we also can do by constructing the differential forms, which we go over extensively in my previous series on invariance and algebra, the exterior derivative, d, this simple d will just unify gradient, curl, divergence, all into a single operation, okay? And crucially, d squared is equal to 0. So it's always, that just implies that there's no curl of a gradient or no divergence of a curl. And all of the, the rules or the vector identities that you memorize in, Griffith's E&M textbook or whatever, they all come from this, from the density, or they're encoded within the exterior derivative. We get it for free. Also, Stokes' theorem is just that, the integral of the differential form over a manifold is equal to the integral over the boundary of that manifold with respect to the differential form or whatever. So it just makes it quite trivial or tautological, because of how we have defined the differential forms, or K forms, right? Now, with a metric, we can map the Hodge star will allow us to map K forms to n minus K forms via something called duality, okay? And the Laplace-Beltrami operator is equal to the exterior derivative acting on some little delta, and plus the little delta acting on the exterior derivative to be equal to just, the square of these two operators, with delta to be equal to the exterior derivative. So this will solve heat/wave equations on any manifold, and we can see it via Hodge decomposition. So any form with a metric, endowed with a metric, splits into an exact exterior derivative and a coexact little delta acting on something, and a harmonic form, okay? And so this is the harmonic form delta, and this is called the codifferential, okay? Now, this allows us to solve the heat equation or wave equation on arbitrary manifolds, from donuts to black hole horizons, and we can see this here. So if we look at the original vector field, right, on this on the sphere, all right, what we can do is, again, the sphere is endowed with a metric, right, in general, and we can look at how the exact well, first of all, we can decompose it into its exact form, and the exact looks very what does it look like? It looks gradient like, right? It looks like irrotational. There's no rotation happening in the exact part, which looks very fun. I mean, this is fundamentally what we talked about, and this connects to the very first integration by quadrature episode, right? But if we also look at the coexact component, we can see the rotational parts of the components acting on this manifold, and this ties back again to how the exact forms and the coexact forms, and for a sphere particularly, the harmonic form is going to be constant. And the reason why is because it's genus 0, right? It doesn't have any holes on it, all right? But if we look at a torus, for example, we get a harmonic form, and we get a non-zero constant vector magnitude across, okay? And, we can also investigate as well the coexact, the exact component, and look at the original vector field that we were composing to begin with, right? And just for fun, let's look at a Mobius strip, okay? Mobius strips also, again, it's for arbitrary manifolds. This is just kind of to show you that, like, you can do this. This is what Hodge decomposition allows you to do, is to encode the vector fields and decompose them into their exact and coexact parts and their harmonic part that depends on the genus of the topological space, okay? So there's a harmonic component. It's just constant, okay? Great. Now, this ties back forms, right, to make conservation geometric and invariant, like our covariant derivatives. And on curved spaces, the Hodge operator, or the Hodge star operator, will reveal topology and echo holonomian. But now we need to connect waves to geometry. All right, we need to turn waves into geometry, and this is where optics and rays come in. So, what are rays? What are optics? You can't really rigorously understand what optics or waves are until you understand the WKB approximation and the failure of the WKB approximation. Okay, so again, high frequency waves. What is the WKB approximation? We talked about this in the very first episode of the series, but the high frequency waves with some short lambda act like rays, right? And these are the geometry for the PDEs. But if you remember, we stuck this together with the Airy equation, or with perturbation theory. I'm sorry, it wasn't with perturbation theory. It was to tame the divergence that was happening from the high frequency waves, because they were blowing up to infinity. But again, if we start from some wave equation, let's say the Laplacian of u minus some 1 over c squared, where c is this finite idea of finite propagation that encodes the Lorentz symmetry of the space, the WKB ansatz is going to give the iconal equation. So if you substitute the ansatz itself, or the approximation, you get the iconal equation for phase phi. And then this is a first order PDE then that we solve by method of characteristics. So again, also relates back to the concept that I said, partial differential equations, you just solve them with ordinary differential equations. And guess what? We encode the WKB ansatz to get the iconal equation from the wave equation. All right? And this gives us light rays, which happen to be things that we call geodesics of the system. All right? So let's look at light rays. They can bend and focus around things that we call caustics. All right? And these are envelopes of brightness where the WKB approximation fails, the caustics themselves. And so we can look at then, we'll try to visualize this where again, at these points, or at these loci, the ray approximation breaks down. We have amplitudes that blow up to infinity, so we have to return to the full wave theory, or the Airy functions of the first episode. So again, we will look at incoming rays that bend inwards, and they focus pre-lensing. And if we increase the curvature, so let's increase the curvature of the lens, we will see that the higher curvature sharpens the focus, and it forms a brighter Caustics curve. And this kind of gives us like the coffee cup like rainbows, if you've ever seen those things. But if we add rays, we can also add rays to this to see how essentially this envelope is clarifying. All right, and this links everything, because rays then are characteristics, okay, or parameterizations of the ODE, right, to follow particular paths that comes from conservation and hyperbolics, right, bending by gradients and covariant like gradients on these manifolds of some varying number of rays, right? And the caustics are shocks. Okay, these are little shocks in the optics themselves, from that are nonlinear, where the waves start to become a lower frequency and reclaim the dominance. So again, we've escaped grids, we've tamed the curvature with connections, and we've handled shocks invariantly. We've unified calculus geometrically, and we've seen waves become rays themselves. Okay, so that's what a ray is. They're very deeply geometric objects that depend on differential geometry, and solving ordinary partial differential equations on curved manifolds. And these concepts, they all interconnect, right? Invariance, the whole idea of invariance, physics being invariant, is the thread, right? From holonomy, measuring curvature, to forms, enforcing the conservation on any space. So thank you for joining me on this episode, and you can play with the interactives in the notebooks after I finish uploading everything and refactoring all the notebooks and uploading it to GitHub. But again, if you have any questions, drop them below, drop them in the Discord, and I'll see you in the next video. Thank you.